We move on to the next speaker, who's our very own Rajesh Ravindran, who is a faculty member at the Institute of Mathematical Sciences. So, Professor Rajesh did his undergraduate, got his undergraduate education from IIT Kanpur in physics. He then got his PhD from TIFR, in what was then Bombay, now Mumbai. And he had postdoctoral research stints at Oxford and at Brandeis universities. And since 2005, he has been a faculty member at the Institute of Mathematical Sciences. So he works on many interesting things. He works on powders, granular matter. One of his most recent research projects was on the rock sizes in the rings of Saturn. He also works on bone structure, how our bone structures adapt to support weight, and about packing of differently shaped objects in general. So he will talk to us about one more exciting existential question. What is time? Why does time go forward? What does it mean for time to move forward? We will have him on stage in a bit. Meanwhile, please do keep sending us questions. We have some questions we've posed to our speakers. We will have another session at the end of all the 4 talks where we'll have all the 4 speakers on stage. We will pose your questions to them. So do keep sending us your questions by SMS, Facebook, or Twitter. The details are on the program sheet that you've got. We'll also flash them again if time permits. Good. On that note, over to Rajesh.
Thanks, Ganesh, for the introduction. Let me start by thanking the organizers for giving me this opportunity to speak about in front of this audience. Not only is it very large, but there's a very mixed makeup, making me quite nervous. Secondly, I would also like, it's a privilege to speak in front of many young people, some of whom I hope will be the ones doing the cutting-edge scientific research in the future. Okay. But young or old, we have always wished sometimes that if you could go back in time and erase some of the blunders we have made. But the question is, do the laws of physics allow us to do that or do they not? Even though we know we cannot do that, do the laws of physics allow us to do that? A variant of this question is at the foundations of an area of physics called statistical mechanics. I'll try to pose the question and try to explain why we cannot go back in time. So let me start by showing 2 movies. Okay, that's movie number 1. And that's movie number 2. Okay. One of them is played forward and one of them is played in reverse. How many of you think the first movie was played in forward? Okay, so a lot of you think the second movie was played in forward? No, none of you think the second movie was played in the forward direction, because we all intuitively know that so in this movie, I hit a Rubik's Cube, the Rubik's Cube starts moving, it has some energy which we call kinetic energy, but it's sliding on some board, there's friction between the board and the Rubik's Cube, after some time it comes to rest. Okay. But we're all taught in school that energy is conserved. So where did that kinetic energy go? That kinetic energy went due to friction. Some heat is produced. The board gets heated up a bit. The Rubik's Cube gets heated up a bit. All those particles start jiggling a bit more. Okay. In the second movie, all that kinetic energy that went into the board recouped itself, went into the Rubik's Cube, and the Rubik's Cube started accelerating and going back, which we know will never happen. Okay. Now, a similar, just to reiterate the point, a glass of water, I drop a drop of ink. After some time, the ink becomes more or less totally, the solution becomes more or less homogeneously blue. And the reverse movie looks as unlikely as anyone can pick out that this is the reverse movie. So now the question, so there is nothing unobvious about these 2 movies, but what I like to ask is, do the laws of physics allow both to happen or just one of them to happen? Now this example is a bit difficult to analyze, so I'd like to make a simple model for liquid ink in water. So first thing I like to do is replace water with some red spheres, replace ink with blue spheres, and then just say these balls move around, and when they meet each other, they collide. And they collide according to the rules of collision which we learn in school. Now you might say, but a water molecule does not look like this. A water molecule has 2 hydrogen atoms and 1 oxygen atom. But when you make a model, you want to make a simple model which you can analyze. And the validity of the model depends on whether it's able to reproduce the phenomena that you're trying to model. So we like to ask, if I make a model like this, does it obey the mixing and the demixing property I showed earlier? Okay. So if I play this movie, after some time, the blue balls and the white balls, red balls mix up. So I'll give a name for this mixed up state. Red plus blue is like purple. So this is a purple state, the mixed up state. And if I run this movie in backwards, the purple state goes back to a red blue state. Okay. So I'll refer to the original state as red blue and the second one as purple. So I like to ask, so one of the movie we know doesn't happen, the other one we know happens. Okay. So where is it that this forwardness in time and the backwardness in time come about? So one thing that you may say is that maybe when particles meet each other, they interact, they already have an inbuilt sense of time in them. So if you want to analyze that further, I take a particular snapshot of the configuration. It's a mixture of blue and red, purple. I take a small region in the middle and let me expand that out. Okay. So in that small box, there are a few blue balls, some red balls. Most of them are away from each other and they're moving in a straight line. But also sometimes 2 particles collide. These are the only possible interactions in the system. Okay. So what I want to ask is, if you track these interactions carefully, are these interactions themselves knowing what is forward in time and what is backward in time? If each interaction knows what is forward in time and what is backward in time, then there is no problem. What I put in, I get out. Okay. But if this interaction do not know what is forward in time and backward in time, then I'm in a bit of trouble because I didn't put that in, but all of you are able to tell which movie is forward and which movie is backward. Okay. Okay. So let us look at the 2 motions. This is a single particle. It's moving in a straight line. At this particular point, I take this particle and reverse its velocity. And it comes back to the original point. Okay. If I show you this movie, you won't be able to tell me which one was the forward movie and which one was the reverse movie. Okay. So that's one motion. The other interaction was 2 particles come, they meet each other, they go off. But if I reverse the velocities, they come back and go. Okay. So reversing the movie is like reversing the velocity of the particles. Velocity means the speed, I just make the directions opposite. And if I look at each individual collision or each individual motion, I cannot tell you what is forward in time and what is backward in time. Okay. But then you may argue that maybe collisions, real laws are more complicated than just colliding particles. But I can tell you that most laws in physics, the fundamental laws, do not care whether time is going forward or time is going backwards. If I reverse the velocities and make the time run backwards, the movie looks exactly the same as far as the laws of physics are concerned. So that raises this question. While you are able to distinguish which movie goes forward and which one backwards, the laws of collision do not make this distinction. Okay. Here lies the paradox, or which as a scientist, so one way out is to argue that, oh, you have fundamental laws of physics, but when you see large amount of particles, you put in another law. But that is not acceptable to a scientist. Scientists would like to ask, from as few principles as possible, can I explain nature? Okay. So one would like to ask, why is it that the laws of physics do not make a distinction between forward and backwards, but we are all able to tell what is future and what is past? So this question was answered in detail by this person, Boltzmann, who laid the foundations of this field called statistical mechanics. So I will try to explain. So is the question clear to everyone? The contradiction is exactly this. The laws of physics do not know what is future and past, but from experience we all know what is future and past. Okay. So let me start with a simple question. So I have a purple state, a mixture of blue and red. There are some green in there, you can ignore them. And I let this movie run for some time, and I want to ask the question, is it possible that at some point suddenly the blue come to one side and the red go to another side? What are the chances of that happening? Okay. Again, you look at this movie, it's very difficult to say. I do not know what the answer to that is. So when you do not know the answer to that, a complicated problem, you make it even simpler. But don't make it too simple, but you can make it simpler so that you can understand something, and then you make it more complicated. Okay. So rather than take all these 200, 300 particles, I take 4 particles. 2 blue and 2 red. The blue on the left, the red on the right, and I put on a computer and let it evolve in time. Okay, they move around. Now 2 blue on this side and 2 red on this side. Again 2 blue back here, 2 red back here. So in this particular movie, even though I started every now and then you get a phase where blue and the red separate out. Okay. So maybe I can analyze this movie a bit better to understand why is it possible to reverse things in this, or is it not possible to reverse? Okay. Okay. So first thing to do is I keep on looking at particular snapshots of the movie. Okay. And then whenever 2 reds come on one side and 2 blues on one side, I say 1 run has been scored. So this is like these bar charts they show in cricket commentaries. These are over and above 2000, 2100 and so on. Whenever you see 2 blue on one side and 2 red on one side, you put 1 run. Otherwise it is 0. Okay. So this particular plot just says that every now and then I see 2 blue on one side and 2 red on the other side. Otherwise I see some other state. Now given this particular information, so the other information you can get is run rate. You ask, at what rate do I score these runs? So you take the number of successes you get, divide by the total number of things you look at, or look at the number of runs you scored by the number of overs you have bowled, and you get some curve like this. This is something you're all familiar with. Sometimes, you have a batsman like Tendulkar batting in the beginning. The run rate is quite high, but after some time, by the 50th over, it sort of flattens out. Sometimes you have somebody like Ravi Shastri batting, then it would have started from here, but always towards the end of the 50th over, it comes to the rest. For many of the younger people, maybe they don't know Ravi Shastri, but I grew up with Ravi Shastri batting very slowly and frustrating, but that. Okay, so then I look at this number here. It looks like a nice number. Can I make a guess what that number could be? And then I plot this number 2 by 16 along with this line, and it sort of matches very well. Okay. Now 2 by 16, as a scientist when you look and see, you see 2 by 16, you see maybe I can give an explanation for 2 by 16. If it was root 2 by 16, I would think maybe I cannot tell. But 2 by 16 is a nice number. So you think, okay, maybe there's a simple explanation for this 2 by 16. So I take the box, I put a line in the middle, and I don't care what is the position of the blue and the red particles. I just ask, are the blues on the left or are the blues on the right? The position, I care left and right, not more than that. Then I ask, how many ways can I put the blue balls? Both the blue balls can be on the left, both the blue balls on the right, one on the left, two on the right, two on the left, one on the right. There are no other possibilities, 4 possibilities. Okay. Now for each of these possibilities, I ask, where can I put the red balls? So I take the first case of the blue balls, both blue balls on the left, in all the 4 cases. For each of these possibilities, I can put the red 1, 2 on the right, 1 here, 2 here, 1 here, 2 here, and 1. There are 4 ways of putting the red balls for each of those, each position. When I put the blue balls on the left, there are 4 ways of putting the red balls. Okay. But remember, I could have put the blue balls on both right also. I repeat the red configurations, I get 4 more. Then I put the blue ball 1 on the left, 1 on the right. Then I repeat the red positions, I get 4 more. I put 2 here, 1 here. I repeat the red positions, I get 4 more. Okay. 16 total. Out of which I ask, in how many configurations are the 2 reds on the left, and how many configurations are the 2 reds on the left and 2 reds on the right. This satisfies that and this satisfies that. Okay. So what fraction of the configurations of all the configurations allowed are two colors on the left and 2 colors on the right? It is exactly 2 out of 16. Okay. And therefore, that's precisely that number that came here, 2 by 16. Okay. So it is as simple as that. If I make a simple counting like this, the answer seems to match very well. Why did I do this counting? So that, so let me now make it a bit, I cannot, if I have 6 particles now, I will find it difficult to count all of them. If I have 8 particles, even more difficult to count. So rather, let me think of this in another way. I take the first blue particle, I throw a coin. If the coin is tails, I put the blue particle on the left. If the coin is head, I put the particle on the right. So a blue, blue, red, red corresponds to tail, tail, head, head, or it would be head, head, tail, tail. These are the only possible combinations of coin tosses where 2 blues will come on one side and the 2 reds will come on the other side. In all other combination of tosses, I get some other configuration. Okay. So now you know that when you do go for a toss or something, it's very difficult to always be correct. If you want to get the reds on the right and the tails on the left, you have to make the correct call many times, which is very unlikely. Okay, so if I were to do 6 balls, I need 3 heads or 3 tails, 3 heads, or 3 heads, 3 tails. Okay, the answer becomes 2 by 64. If it is 4 particles, 8 particles, I get 2 by 128, and so on. Okay. To make more sense of this, suppose I see frames at the rate of 1 frame per second. Okay. You ask, how often would you see all blue on one half and all red on the other half? So, if there were 10 particles, you would see once every 8 minutes. If you put 20 particles, you would see once every 6 days. If you put 50 particles, you would see one every 6 billion years. Okay. Now that is like the age of the earth. Okay. Now you may say, that's okay. How many water molecules are there in that container? Maybe there are 10 of them. But the answer is, there are about this many water molecules in that small container that I showed. This is 1 followed by 23 zeros. So once you extrapolate this, I do not know how long it will take. Even if you measure the rate of 1 billion frames per second, there is no way you will ever see a separation of blue on the left and red on the right. It is only because the number of particles as it increases, the chances of this happening keeps going down and down and down. Okay. Okay, there is almost no chance of ever being able to see a separation of red and blue. But then, sorry, and, what has this taught us? So I initially asked, can I tell the arrow of time or which way the time moves by give some explanation for that? Have I given an explanation? No. I have posed a different question and answered that. If I showed you that movie which I showed you earlier, then you wouldn't be able to anyway tell what is forward in time and what is backward in time. Because I started with the purple state. So I answered another question. I answered, if I start with the purple state, how will I know, will I ever go back to a red blue state? But that does not answer why, if I start with the red blue state, I'll always go to purple state. Okay. So I need to answer that question too. So the perception of what is forward in time comes only because you started the state in an ordered state, where red was on one side and blue was on another side. And as time went on, it became more and more disordered. Now, if I played a reverse movie where I took the disordered system, which is the purple state, I reversed the velocities and went to a red-blue state. Now I take the same configuration, which went back to that, but I take these green particles and just move them around slightly. I make a small perturbation. I say I don't do exactly what I want, reverse the velocities. I reverse the velocities of all the particles, but not these green particles. And I ask, do I go back to the red and the blue state, or do I go back to some other state? Okay. It keeps going on and on. It is trapped in the purple state. So if I ask if an experimentalist tries to ask, can I prepare a state very carefully so that I go from a purple state to a red blue state? It is possible, but it's extremely difficult to do so. And the number of and if you try to make the smallest error, it does not go back to an ordered state. It goes back to the disordered state here. This would not be true if the number of particles were 2, 3 or 4. This is true because the number of particles are of the order of 10, 1 followed by 23 zeros. Okay. I hope I conveyed some, okay. So let me go back to this example here. So here you may ask, what happened? Why can't the reverse movie be the true one? So I put energy, so in this case, like the particles when you put them left and right or you make them homogeneous, the number of states available for the purple state were much more. Here, the energy, the kinetic energy of this particle, when you disperse it into the surroundings as heat, when all the molecules jiggle, there are a huge number of ways of doing that. While if the particles are moving in unison, there are very few ways of doing that. So, if you make a rule which says that the world would like to be more and more disordered with time, then this movie is preferred over the other one. Okay. So, you might ask, this seems to be a problem that's not very important, you know, whether we all intuitively know what's the direction of time. But if this particular phenomena which I told you, as the number of particles increase, this law that things become more disordered with time is true, then this particular thing has profound consequences for engines, for example. If I ask, can I make an engine 100% efficient? Can I, with the petrol I put in, can I convert it completely into kinetic energy? Answer is no. It puts constraints on what you can do with machines. Okay. Now, so what I tried to argue was that if I put in more and more number of particles, then you know if something comes out, some emergent phenomena comes which says I know what is forward in time and what is backward in time. Now let me ask a more general question. Is this irreversibility the only consequence of a large number of particles? That is not true. Every time you put a collection of particles together, some new phenomena appear. For example, if I take molecules, and put them together, I might get a polymer. If I put polymers and put them together, I get cells. If I put many cells together, I get animals, human beings. I put many animals together, I get a society, and so on. Every time I take a step from molecules to polymer to cell to animal to society, something new comes. For example, when I put cells together to get animals, I get life, I get emotions. When I put animals to society, I get culture, jingoism. But at each level, I do not know what I will get at the next step. So the role of condensed matter physicist or a statistical mechanics person is to ask, how do I go from one step to another step? I put many together. What are the new phenomena I see? How do I go about calculating these new phenomena? Now the world around you is all made up of objects like this. So there are a lot of things to study. For example, you sit on a chair. A chair supports your weight. You move it like this, it does not move. Where does that property come from? That property came from putting together many molecules together. So we study and ask, how do the material, for example, mechanical properties of a chair come from? Okay. So, for instance, molecules can exist in the form of solid or liquid. Now, these come about because of a more complicated interactions than from what I showed you. But we tried out this movie. So, we take a small dish, take some ball bearings and vibrate them. They just roam around like that. Or you put more molecules, more ball bearings and shake them, they form a nice pattern. There's for each molecule, each ball bearing has 6 ball bearings around them and they form a regular structure. Now that is what you study in school. A solid is something where molecules are arranged in a regular pattern. Okay? So these are macroscopic particles. But now, if you are curious enough, you can ask, if I were to change the shape of these particles, for example, instead of spheres, I make them cylinders, or I make them banana-shaped particles. What kind of solid structures do I get? What kind of mechanical properties do I get? Now that turns out to be an active research area. Or you can ask, I take some of these spheres and make them double the size, some of them half the size. Okay? And then it becomes something called a good model for glass, the glass that you see around. And that is another research area which is very active. Okay? So you have to just ask the right question and you jump into a active research area. So, the moral is that when you put in large number of particles, you can get phenomena which you never expected from knowing the interaction between two particles. So all this while, I talked about particles which had no life, the inanimate objects. But now, let me leave you with a movie made up of living particles. So this is a movie of some birds called starlings. They move around. Okay. So huge number of birds, when you put them together, they move in nice flocks. These flocks change directions rapidly, left and right. Sometimes it becomes more dense, sometimes it becomes less dense. So you can ask, how does this come about? Have they practiced beforehand like a march past? That doesn't seem very likely. So each bird is just looking at a neighboring bird. Maybe it just looks at a neighboring bird and tries to follow that. Maybe it looks at few more birds around it and follows that. Okay. So, but just by doing some local interaction, you can get complicated behavior where the whole flock changes direction rapidly from left to right. Now, these birds are a bit different from the balls I showed you because they have some intelligence of their own. They take in energy and then they move by converting this food into mechanical energy. Understanding the motion of such massive objects, which does not depend on the motion of the individual particles, but as a whole there's a motion, is again an area of active research. Okay. So the moral of the story is, when you put things together, it is not just enough to know the interaction between two particles. What you get is sometimes very surprising. And that is what people in condensed matter and statistical mechanics like we do as a regular research. And it's quite exciting because what you find is often what you didn't expect from before. I'd like to stop here.
Thank you, Rajesh, for that very nice talk, all those beautiful simulations and videos. So we have a few questions for you. So here's a question that came through from the SMS from the phone number which ends with 398. It says, you showed that the red-blue state will return after some time, even though the probability of this is very low. But then the entropy will decrease, but we know that the entropy always has to increase. So what is the resolution?
Anyway, I didn't use the word entropy.
Yes, so
throughout.
clearly this is somebody who's studied things beyond the syllabus. But you can...
So if I wait long enough, you may have some situation where entropy decreases, but the chances of that is very, very low. So if I take smaller and smaller systems, not 10 to the power 23 particles, but let us say I take 100 particles, you will see this more and more often. And modern experiments where they do experiments on polymers and nano systems, you do see these entropy decreasing activities, and that is exciting. But when I make number of particles go to a container of water, it never ever happens.
So the law that entropy will increase is not always true. It's true for larger systems.
It is true for larger systems, and it becomes a certainty for large systems.
For very large systems. Good. Okay, let's move to the next question by Vishwam Shankaran. Can the study of emergence of properties at the molecular level help us understand the rules of interactions at the cellular level or at the level of cities? So is it possible to understand rules at bigger levels from the study of smaller systems?
Yes. So suppose I want to study, as the example I gave of societies, and I start from humans, I go backwards to cells. So ideally, you should be able to look at the interaction between cells and try to predict how humans should behave. And by looking at the way humans should behave, you should be able to predict how society should behave. Then you put societies together, you should be able to predict the other one. So this coarse graining from small to large does happen. It's difficult, but many of us do that too.
So it's possible and works. In some cases it works. It's possible to actually
in some cases it
reduce the rules at a higher level than this.
In the example where you start with two water molecules, you do the quantum mechanical solution, you find the interaction between them, you put them together, you get next level of network of water molecules, you put network of water molecules together, you get higher one, you do that, yes.
So this perhaps related to the next question from Tyagarajan Tyago. So this analysis of particles in time seems to have close connections with finite element analysis. Is this true? Or maybe I could just go on, extrapolate this one a little bit. So suppose you're an engineer and you want to study the reliability of a chair, for instance. How do you go about studying? So should you really go down to the level of molecules? Should you go down to, how do you decide where to draw the line?
So at the level of the reliability of a chair, for example, what works best is something called continuum mechanics. But continuum mechanics already is a coarse grain level of molecules, is a level beyond molecule. It works at the level of micro scale. There are already huge number of molecules, and you write a coarse grain this and get some theory at that level, which you put together to get the failure of a chair. So if you do start from molecules, you do get better understanding, but that doesn't have to be the case.
Very nice. Good. On that note, let's thank Professor Rajesh again. Thank you for that very nice talk.